One of the biggest changes in the way vehicles are serviced is the increasing use of computers in diagnosis, made possible by the increasing use of onboard computers to control automotive systems. Despite this trend, some automotive service skills have remained the same, and one in particular continues to rely on precision measuring tools for information. We're talking about measuring basic engine dimensions, dimensions that can tell you whether a part or assembly is fit for service or needs to be repaired or replaced. Welcome to this MasterTech release on basic engine measurement. When it comes to engine parts, it doesn't take much of a difference in size to make a big difference in operation. Take these bearing shells, for instance. One shell is only 0.02 of an inch thicker than the other. Yet 0.02 of an inch is about the right thickness for the film of oil that keeps the bearing shells from contacting the crankshaft journals. So if the bearing shell is 0.02 too thick, there's no film of oil. And if it's 0.02 too thin, there's excessive clearance. So you can see why it's essential to determine the exact dimensions of engine parts. In this program, we'll be measuring those parts using a variety of precision tools. But before we measure anything, we need to look at a few things that can affect your measurements. It doesn't do much good to measure parts precisely if you're unsure exactly where they go. So number parts prior to disassembly, or put them in order during disassembly. You also need to make sure you are measuring actual parts and not gasket material or accumulated crud. So make sure parts are clean before measuring. Our final precaution is one you may not have thought much about, but you've probably used the underlying principle in disassembling hard-to-remove parts. What it boils down to is that because parts change size with temperature, you should make sure they are not excessively hot or cold. In fact, they should be as close to room temperature as possible. Next, we'll take a look at one of the most versatile of the measuring instruments, the micrometer, and a tool that is often used with it, the telescoping gauge. Micrometers, or mics as they're often called, are among the most versatile and precise of measuring tools. Objects to be measured can be inserted between the anvil and spindle of outside micrometers. Inside micrometers can be inserted into a space for measuring inside dimensions. And depth micrometers can be positioned on flat surfaces to measure depth. In this program, we'll concentrate on outside micrometers, since they're involved in more of the measurements we're interested in making. However, keep in mind that the operation of inside and depth micrometers is similar, and you can apply the information about outside mics to these measuring tools as well. We've mentioned the anvil and spindle that objects are inserted between on outside micrometers. Other parts include the frame, which supports the anvil and spindle, the sleeve, which contains the larger graduations used in measurement and possibly a vernier scale, and a thimble, which is rotated to advance and retract the spindle, and which also contains smaller graduations. Some micrometers also have a ratchet stop device to aid in taking uniform measurements, and a device for locking down the spindle. Most good micrometers have standards of a specified size that allow you to check accuracy. How you read the measurement on an outside micrometer depends on what type you're using. On non-digital micrometers, which read in inches, each tenth of an inch is assigned a number. Vertical lines divide each tenth into quarters, or 25/1000ths of an inch. So the first vertical line to the right of the 1 represents an additional 25/1000ths. The second represents an additional 50/1000ths, and so on. When the 0 mark on the thimble lines up with the horizontal line on the sleeve, the reading is an exact multiple of 25/1000ths. But what if the reading is between, say, 125 and 150/1000ths? Lines on the thimble divide it into 25 parts. These divisions allow you to determine the number of thousandths that need to be added to the reading on the sleeve. Now let's apply this information to a sample reading. The thimble is between the 3 and 4 on the sleeve, and also between the 50/1000ths and 75/1000ths marks. So we have 3/10ths of an inch plus 50/1000ths. We also have an additional 20 thousandths on the thimble. So our total reading is 3/10 plus 50 thousandths plus 20 thousandths, or 370 thousandths. Some micrometers also have a vernier scale on the sleeve, which allows you to measure to 10 thousandths. On a vernier scale, the line on the sleeve that lines up with the line on the thimble indicates the number of 10 thousandths to be added to the reading. Now let's go back to our 370 thousandths reading and add any additional 10 thousandths. As you can see, the line corresponding to the 8 lines up. So 8 10 thousandths must be added for a total reading of 0.3708 inches. Keep in mind that had the 20 mark on the thimble lined up exactly with the sleeve, the 0 marks on the vernier scale would have lined up, indicating that no 10 thousandths needed to be added. Also, keep in mind that we need to add in the inch range if the micrometer is not a 0 to 1 inch micrometer. So the reading on this 1 to 2 inch mic is 1.3708 inches. You can read metric micrometers in a similar way, but the graduations represent different dimensions. The sleeve is graduated in half millimeter increments, with every 1/5 millimeter called out. The thimble is graduated in hundredths of a millimeter. A vernier scale graduated in 1 or 2 thousandths of a millimeter may be included. So the reading on this metric micrometer is 12 millimeters plus 0.5 millimeters on the sleeve plus 32 hundredths on the thimble for a total of 12.82 millimeters. The vernier scale gives us an additional 6 thousandths for a total of 12.826 millimeters. One common use of the outside micrometer is measuring the connecting rod and main bearing journal diameter of a crankshaft. Crankshaft journals may have been worn or ground down to an undersize, and measuring the journal lets you determine this. For example, for the 3.5-liter engine crankshaft, normal undersized dimensions include journals that are 1, 2, 3, 10, or 12 thousandths of an inch smaller than standard diameter. You also need to check journals for an out-of-round or tapered condition. These conditions are the normal result of uneven loading. To check for them, take 3 measurements of journal diameter, 120 degrees apart at one end of the journal. Repeat the measurements at the middle and the other end of larger journals, and merely at the other end of smaller journals. Out of round is the maximum difference in any particular set of measurements separated by 120 degrees. Taper is the maximum difference between any 2 readings taken at the same location along the length of the journal. To determine if a repair is needed, compare the journal measurements for out of round and taper to the specifications in the appropriate service manual. A typical limit on taper and out of round on a crankshaft journal is 1/1000th of an inch. You can use the same method to check a camshaft journal for excessive wear or out of round. Let's check out a main bearing using the information we've just discussed. We take and record measurements at 3 different points, 120 degrees apart at one end of the journal, moving across the journal for the next 2 sets of measurements. Note that we're using a micrometer with a ratchet stop thimble that helps produce uniform readings by limiting the pressure on the micrometer's contact faces. With all 9 measurements made, we can now calculate maximum out of round and taper. Notice that maximum out of round and taper do not exceed 1/1000th of an inch. Also notice that the main bearing journal diameter is within 1/1000th of the standard size. The journal is not undersize. You can use an outside micrometer with our next tool to measure inside dimensions. The telescoping gauge, also called a hole gauge, has spring-loaded plungers that can be pushed in while the gauge is inserted into a hole. When the gauge is positioned at the spot you want to measure, you simply lock the plunger position by turning the locking screw on the gauge handle. After the plungers are locked, you can use an outside micrometer to measure the dimension. When used with outside micrometers, telescoping gauges are useful for measuring various bore diameters, However, you need to use these tools carefully, since such indirect measurements are more prone to error than ones made directly. So, when measuring a cylinder bore, for example, you can help ensure an accurate reading by positioning a piston in the cylinder and placing the gauge on top of the piston so that it's straight across the bore. Other uses for a telescoping gauge include measuring connecting rod and main journal bearing bores for an out-of-round condition. To check a connecting rod bore, clamp the rod in a soft-jawed vise. Install the rod cap without the bearing shells and tighten the cap fasteners to the specified torque. Use the telescoping gauge and micrometer to measure the bore in 3 places that are an equal distance apart. To determine out of round, subtract the smallest measurement from the largest one. To check main bearing bores for an out of round condition, remove the crankshaft and main bearing shells and tighten the main bearing cap fasteners to the specified torque. Since they're not on the ends of pistons and have a larger diameter to distribute the load, main bearing bores need to be checked in only 2 locations to determine out of round. Now let's use this information to check a main bearing bore for an out-of-round condition. We first insert the gauge perpendicular to the cap parting line and lock its plunger. Then mic the gauge and record the measurement. Next, we insert the telescoping gauge into the bore with one contact just above the cap parting line and the other contact just below it. And again, mic the gauge and record the measurement. As you can see, the difference between the measurements is negligible, and the bore is not out of round. Next, we're going to look at an easy way to measure bearing clearance. But before we do, try this review question. Given the measurements of a main bearing journal diameter shown here, is the journal within the allowable limit of 1/1000th of an inch for out of round and taper? You'll probably need to pause the tape at this point to answer this question. The answer is no. At 2 locations, out of round is considerably more than 1/1000th, and taper is also outside of allowable limits. When you think of measuring a few thousandths of an inch of oil clearance and how important that clearance is, you can see why it might be very useful to have a tool that is easy to use and specially designed to give accurate results. That tool is Plastigage. The principle behind Plastigage is simple. Plastigage is inserted between parts which need to have a specified clearance. As fasteners are tightened, clearance decreases between the parts, flattening the Plastigage. The piece of Plastigage becomes wider as it flattens, and this width increases as the clearance decreases. By comparing the width of the flattened Plastigage to a scale, you can tell what the clearance is. Plastigage comes in various sizes, and you need to select the range that is most likely to match the clearance you're measuring. For example, shown here are 3 size ranges, which can measure from 1 to 9/1000ths of an inch clearance. There are several precautions to keep in mind when using Plastigage. First, Plastigage is sensitive to heat, so make sure parts are not warm or hot, or the Plastigage may be deformed or melt. Second, Plastigage dissolves in oil, so be sure to clean oil from the parts to be measured. Third, make sure parts do not rotate during Plastigage checks. Rotating parts smear Plastigage, making readings inaccurate. The most common use of Plastigage is for checking main and rod bearing to journal clearance. Let's look at what you need to be aware of when checking clearance on main journals. If the engine is in the car or right side up on the engine stand, the weight of the crankshaft may affect measurement. You can use 2 methods to remove any clearance between the upper shell and the crankshaft. The preferred method is to place shims between the lower bearing shells and caps of bearings adjacent to the one to be measured. For instance, here bearings 1 and 3 are being shimmed with matchbook covers so that number 2 can be checked with Plastigage. The appropriate service manual contains a list of which bearings to shim when making checks. The service manuals also list an alternative method of propping up the crankshaft with a jack stand. Now, if the engine is out of the car and inverted, you don't need to support the weight of the crankshaft. At this point, let's run through the actual steps to check clearance on a main bearing journal on an engine that is inverted on a stand. With the bearing cap and shell removed, we wipe the journal and then place a strip of Plastigage across the entire width of the journal, being careful to position it away from the oil holes. If the engine were in the car, we would place the Plastigage across the bearing shell. Next, we install the bearing cap and shell on the crankshaft and tighten the fasteners to the specified torque. Then, after removing the cap and shell, we compare the width of the Plastigage to the scale. In this case, clearance turns out to be about 1/1000th of an inch. Plastigage can also indicate taper. If the strip is wider at one end, the clearance is not uniform from one end of the bearing to the other. Measuring clearance on a rod bearing journal is similar, except you do not need to worry about the weight of the crankshaft. Before making the measurement, position the crankshaft so that the piston moves just past bottom dead center. Now that we've looked at Plastigage, see if you can answer this question about its use. Which of the following is something which has to be avoided when using Plastigage? A, oil, B, heat, or C, parts rotation? The answer is all three. Plastigage is oil soluble, can deform with heat, and can be smeared by parts rotation. Like micrometers, calipers are versatile measuring instruments. With calipers, however, you can use the same tool for outside dimensions, inside dimensions, and depth. All sliding calipers measure by means of one or more fixed jaws, and one or more jaws which slide over the caliper body. In the past, in addition to supplying inches and tenths of inches on a bar scale on the caliper body, sliding calipers used a vernier scale, which required you to match up lines to arrive at thousandths of an inch. In recent years, these vernier calipers have been replaced by dial calipers, which supply thousandths by means of a dial mounted on the sliding jaw. And now digital calipers, capable of reading to 10,000ths of an inch, and which are switchable to metric readings, have been gaining in popularity. Since dial calipers are probably the most common calipers used today, let's look at taking a reading with them. For outside dimensions, place the object to be measured between the caliper's lower set of jaws. For inside measurements, insert the upper jaws into the part to be measured. And for depth measurements, rest the body on the part surface while inserting the tail into the part. Reading the caliper is the same, whether you're checking depth or outside or inside dimensions. Take the inch and tenth of an inch reading off the bar scale. In this case, that's 2 3/10 inches. Then add the reading from the dial. In this case, 58 thousandths. The total is 2.358 inches. Now let's put the calipers to work, starting with measurement of piston diameter. We'll use the digital calipers so we can obtain a reading to the nearest 5/10 thousandths. It's important to measure piston diameter at the proper location. In general, the location is across the skirt, perpendicular to and near the bottom of the piston pin bore. The exact location will vary from engine to engine. The piston we're measuring is from a 3.5-liter engine, so the check is made 3/8 of an inch from the bottom of the skirt. Notice the use of a roller knob to position the slide. The roller slips once the jaws are tight against the part, and as a result, aid in consistent readings. Also notice the lock screw, which enables us to lock the slide in place to preserve the reading. As you can see, the reading is 3.778, which is within the range specified for a standard-sized piston. Let's take a look at another use of the digital caliper, checking a connecting rod bore for out of round. You'll recall from the telescoping gauge section that 3 measurements are taken an equal distance apart, with the rod bearing removed and the cap fasteners tightened to specifications. Using the inside jaws of the digital caliper, we take the 3 readings. Upon comparing them, we find that the difference between them is very small. The bore is only slightly out of round. By now it should be apparent that there is more than one way to measure engine components. Take our connecting rod bore, for example. You can check it for out of round using a telescoping gauge and micrometer, a slide caliper, or an inside micrometer. Which way is best? Whichever way provides you with readings that allow you to accurately gauge the component's dimensions. Next, we're going to look at a tool that makes it easier to check cylinder bores for out of round and taper conditions. But first, try this review question. A connecting rod bore is measured for out of round, resulting in the 3 measurements shown here. If maximum allowable out of round is 1/1000th of an inch, is the bore out of spec? You may need to pause the tape to calculate the answer. The answer is yes. The bore is out of spec. If you subtract the smallest reading from the largest one, you'll notice the result is greater than 1/1000th of an inch. Some of the tools we've already looked at can give you an accurate picture of cylinder bore dimensions. For instance, you could use a telescoping gauge and outside micrometer to measure cylinder wear. However, a specialized tool called a cylinder bore gauge makes it easier to do so and less prone to error. At the bottom of the tool are the gauge contacts. On one side is a fixed contact point. A spring-loaded sled around the fixed point retracts to allow the gauge to be inserted into a bore. On the other side is a spring-loaded adjustable contact point. By adjusting the length of the point, you can set up the gauge to check a particular bore. Above the contacts is a dial and needle, which indicates differences in dimensions as you position the gauge contacts in different parts of the bore. Each graduation of this dial represents 1/1000th of an inch. By holding the adjustable contact in place, a locking handle allows you to preserve a reading, or to set the position of the plunger to a particular diameter, which you can check with an outside micrometer, dial caliper, or gauging ring. Before we discuss where and how to take readings with a cylinder bore gauge, it might be useful to review the normal wear pattern in an engine cylinder. Wear in a cylinder tends to occur along the area in which the piston rings contact the cylinder wall. More wear occurs toward the top of the ring travel area than at the bottom, because there's less oil to provide lubrication. This uneven wear results in cylinder taper. Differences in lubrication and piston loading can also cause a difference in wear from one side of the cylinder to the other, resulting in an out-of-round cylinder. The out-of-round condition is usually most pronounced at the top of the ring travel area. Using a cylinder bore gauge to check for out-of-round is easy. After adjusting the spring-loaded contact, insert the gauge in the cylinder bore, with the gauge contacts perpendicular to the crankshaft center line. Position the contacts at the top of the ring travel area, just below the ring ridge. This is usually the area of maximum wear. Turn the dial until the needle is on 0. Then rotate the gauge until the contacts are parallel to the crankshaft center line. This is usually the area of minimum wear. The difference in the position of the needle indicates the amount of out-of-round. In this case, it's close to 0. Measuring cylinder taper is similar. Start with the bore gauge contacts just below the ring ridge and perpendicular to the crankshaft center line. This is usually the area of maximum wear. After positioning the needle on 0, slide the contacts down to the bottom of ring travel. This is usually the area of minimum wear. The difference in the position of the needle indicates the amount of taper. By comparing the measurements to the specifications in the appropriate service manual, you can determine if the cylinder needs to be serviced. A measurement similar to that for taper can tell you how much the cylinder is worn. Start with the gauge in its beginning position to measure taper. After setting the needle on 0, slide the gauge down the cylinder, but this time slide it slightly below the area of ring travel. The difference between the top and bottom is an indication of cylinder wear. So far, we've been using the cylinder bore gauge to obtain relative readings, which indicate the amount and pattern of cylinder wear. But it is possible to use the cylinder bore gauge to obtain actual measurements of cylinder dimensions. You can do this by locking the adjustable contact point with the bore gauge at the top of the cylinder. Then remove the gauge. By measuring the gauge with an outside micrometer, you can arrive at the bore diameter at the top of the cylinder. Reinsert the gauge and zero the needle. Then, by unlocking the gauge and observing the needle, you can calculate bore dimension. Now let's put our measuring techniques to work with a review question that asks you to determine cylinder out of round and taper. A bore gauge is positioned just below the ring ridge, perpendicular to the crankshaft center line. It is then rotated until it is parallel to the center line. What amount of out of round is indicated here? Keep in mind that the dial is graduated in thousandths of an inch. The correct answer is 4 thousandths. Now try taper. The gauge contacts are just below the ring ridge and perpendicular to the crankshaft center line. The gauge is then slid down to the bottom of ring travel. Once again, the correct answer is 4 thousandths. Our next measuring tool, the dial indicator, can be seen as a general-purpose version of the dial bore gauge. The indicator's spring-loaded plunger, or spindle, is set so its point contacts the item to be measured. When the item is moved, the resulting needle rotation indicates runout, end play, or clearance. Many dial indicators have graduations of 1/1000th of an inch. So, with 100 graduations, one revolution of the needle represents 1/10 of an inch. The total range of the dial indicator depends on the length of the plunger and the graduations used. One useful feature of dial indicators is a rotating dial, so that the zero can be positioned under the needle no matter what the needle's position. This is known as zeroing the reading. Dial indicators require either stands or clamps, so they can be positioned to take measurements. Let's look at using the dial indicator for measurement, beginning with checks of crankshaft and camshaft runout. You can measure crankshaft runout with the crankshaft out of the engine and supported by V-blocks. You can also check the crankshaft for runout while it is in the engine and supported by the end-bearing journals. Position the dial indicator's point perpendicular to the surface of the journal to be checked, and zero the dial. Then rotate the crankshaft while observing the needle. Keep in mind that if a journal is out of round, it will affect the readings. As a general rule, after taking out of round into account, runout should not exceed 1/1000th of an inch between journals and 2/1000ths of an inch overall. Excessive readings indicate a bent crankshaft that must be replaced. Using a dial indicator and V-blocks, you can check camshaft journals in the same way. Maximum allowable runout generally runs from 2 to 5 thousandths. End play is another check you may need to make on the crankshaft and camshaft, and you can use a dial indicator to make this check as well. For crankshaft end play, mount the dial indicator on the front of the engine, with the point resting against the end of the crankshaft. Next, move the crankshaft all the way to the rear of its travel, and zero the dial indicator. At this point, moving the crankshaft forward reveals the amount of end play. Compare the reading obtained with the specifications in the service manual. End play which is excessive indicates either a worn thrust bearing or a damaged or worn crankshaft. Measurement of camshaft end play is similar to that for the crankshaft. Mount the dial indicator so that its point rests against the end of the camshaft. The way in which you check camshaft end play may vary from engine to engine, so be sure to see the appropriate service manual for details. Also, specifications for end play may vary depending on whether you use old or new parts, so be sure to use the procedure for the engine you're working on. Let's look at one more use for the dial indicator, measuring valve stem to guide clearance. For this check, valves are removed from the cylinder head and then inserted to a specified depth in the valve guide. The valve is held in position either with a special tool or with a spacer fabricated for this purpose. The dial indicator is set up so its point is against the outside edge of the valve at a right angle to the valve stem. At this point, you can read stem to guide clearance by moving the valve toward and away from the dial indicator. By comparing the result to the specifications in the service manual, you can determine whether the guide and valve need to be serviced. Now let's apply this information in a review question, in which you're asked to check valve stem to guide clearance. A dial indicator has been set up to check stem to guide clearance on an intake valve. The maximum allowable reading is 16 thousandths of an inch. Is this valve and guide within specifications? The answer is yes. The amount of wear is well below the maximum allowable. We're covering our last two measuring tools together because straight edges are often used with feeler gauges to check for flatness. You can also use feeler gauges by themselves to check for clearance. In a typical set of feeler gauges, thicknesses range from a few thousandths to 25 thousandths of an inch or more. Metric equivalents are also often printed on the blades. Let's look at a few of the clearances on an engine you might check with a feeler gauge, beginning with ring end gap. Ring end gap is the distance between the ends of the piston ring when it is installed in a cylinder. It needs to be maintained within limits. If it's too close, damage to the ring and cylinder wall can result. Too wide of a gap can cause poor sealing. To check ring end gap, use a piston to push the piston ring into the cylinder bore. This ensures the ring remains square. The ring must be at least 1/2 inch from the bottom of the bore. Try inserting different feeler gauges into the space at the ends of the piston ring until you find a feeler gauge that fits, but which still has a slight drag as it is pulled through the gap. This is the size of the ring end gap. Compare the result to the specification in the service manual. Piston ring side clearance is another check made with a feeler gauge. With rings installed on the piston, determine which feeler gauge fits best between the rings and ring lands. Comparing the results to the limits in the appropriate service manual will tell you whether the side clearance is within specifications. Clearance that is excessive indicates worn pistons or rings. Clearance that is too tight often indicates a damaged land or carbon that has not been removed from the piston. Feeler gauges can also be used to check connecting rod side clearance. To do so, find the feeler gauge that best fits the gap between the connecting rod and crankshaft, and compare its thickness to the specifications in the service manual. Excessive side clearance can indicate a worn thrust bearing or crankshaft. You can use feeler gauges with our next tool, the straight edge, to get an idea of how flat the surface of a part is. Of course, not just any piece of metal that looks straight can serve as a straight edge. Straight edges are specially ground to have extremely flat edges. One of the most common uses of a straight edge is checking the bottom of the cylinder head for warpage. To do this, position the straight edge parallel to the cylinder head center line, as well as diagonally across the head, while attempting to fit feeler gauges under the straight edge. Specifications for the maximum allowable clearance are in the service manuals. For example, for the 3.5-liter engine cylinder head we just looked at, the service limit is 8 thousandths. You can use a straight edge to check other cylinder head surfaces for warpage and for checking other components, such as the block deck and intake and exhaust manifold surfaces. Groups 9 and 11 in the appropriate service manual contain procedures for making these checks. Sometimes a straight edge is used without a feeler gauge, such as when checking head bolts for stretching. To check a bolt, place the threads on the straight edge and check for a gap caused by stretched or damaged threads. If there is a gap, you must replace the bolt. Now that we've covered feeler gauges and straight edges, try answering this review question about piston ring end gap. The technician shown here is checking piston ring end gap. What is he not doing that would help ensure an accurate measurement? The answer is that he failed to use the piston to position the piston ring in the cylinder. Using the piston helps ensure the ring remains square to the bore. That's it for this month. The day may come when you can perform a digital, computerized laser scan of engine parts and have dimensions printed out. But until that time arrives, there's no substitute for the common measuring tools we've looked at in this MasterTech. We'll see you next month.